Hello students, this lesson is on rates of change. Graph the data below with time as the horizontal axis. Find and interpret the slope of the line connecting the points. Include units on your answer. So you hire a plumber. The first coordinate is t, which represents time worked in hours, and the second coordinate is capital C, representing the cost in dollars. We'll treat the first coordinate as the horizontal axis, so put time on the horizontal axis and cost on the vertical axis. So when t is 1, the cost is 70, giving us this point. And when the time is 4 hours, the cost is $145, giving us this point. Now we can make a line connecting these data points, and we can find the slope of this line. We'll use m for slope, and you may remember it as delta y over delta x, or y2 minus y1 over x2 minus x1, or this idea of rise over run. The first coordinate is t, that's the independent variable. That's what x normally is. And the second coordinate is c for cost, the dependent variable. That's normally what y is. But let's frame our slope in terms of these variables. It'll be change in cost over change in time. So our second cost is 145. Our first cost is 70. Our second time is 4, and our first time is 1. So we get 75 over 3. And this is dollars divided by hours. And this simplifies to 25. And the units here would be dollars per hour. Now, how do we interpret this number? Now, this is a constant rate of change. It's how much the dependent variable changes per 1 unit change in the independent variable. So in other words, the cost goes up $25 for every hour worked in a proportional manner. So if you work 2 hours, the cost would go up $50, etc. This is, of course, assuming a constant rate of change. Okay, let's go to the next page. A secant line is a line passing through two distinct points of a function. The slope of this line is called the average rate of change of the function over that interval. So we have the graph of some function, we have two different points on that function, and this line here is called a secant line. Its slope is the average rate of change. First, let's set up a formula for finding the average rate of change in this function over the interval from a to b. So let's say the left x-coordinate of that point is x equals a, and the right x-coordinate is x equals b. So the coordinates of that first point would be a, comma, and the best we can say is f of a. You plug a into the function to get the output. And the second point would have coordinates b, comma, f of b. So the slope of the secant line would simply be our change in y coordinates divided by our change in x coordinates, or change in outputs over change in inputs. M is slope, and we have sub SEC to stand for the secant line. And we get that this slope would be the second output, which is f of b, minus the first output, which is f of a, all over the second input minus the first input. And here's a general formula you can use if ever I tell you specifically what the function is and what a and b are. Now there's a second way that we might characterize this, and that's by doing the average rate of change in f over the interval from a to a plus h. So again, let's say that the left x-coordinate is x equals a, but then we're going to go right a certain distance, that distance being h units, to get to this larger x-coordinate, x equals a plus h. So if I use this system of labeling, this first point would have coordinates a, comma, f of a, and the second point, though, would have coordinates a plus h, and then plug in a plus h into the function. F of a plus h would be the representation of the output. Thus, we get the slope of the secant line can be found by doing f of a plus h, which is the second output, minus f of a, which is the first output, and then over the second input minus the first input. But then notice this a and negative a will cancel, giving us simply f of a plus h minus f of a all over h. Now, a tangent line is a line passing through one point of a function, which indicates the function's slope at that moment. The slope of this line is called the instantaneous rate of change of the function at this moment. So once again, we have some function and its graph. We have a singular point on the function, and the line that we say is tangent to the function. It's passing through that point, and it indicates how steep the graph is at that one point. And the slope of that line is called the instantaneous rate of change at that point. Now, it is easy to find the slope of a line connecting 2 points, but the challenge will be how to find the slope of a line if only one point is known. So looking at technology, we have 2 points that are a certain distance apart. Here we have h equals 9. As I shrink h, you can see that the right point gets closer and closer to the left point. Now, when the 2 points become 1, we can no longer calculate a slope because there is only 1 point and not 2. And you notice the line disappears. But if h is really small, like 0.1, and then make it go even smaller, and I'll zoom in, as h gets even closer to 0, the right point gets closer to the left point, and our secant lines get closer and closer to the tangent line. So we are interested in knowing what the slope of this line is here, even when h is 0. However, you cannot simply plug 0 in for h, because you would have division by 0. This is where the idea of limits becomes important. So to find the instantaneous rate of change in f at x equals a, and this point would have coordinates a comma f of a, to find the slope of this tangent line, we are going to use either this formula or this formula, but with an appropriate limit. So in the first case, here's the formula for the secant line using the interval AB, and then we simply want b to approach a. So we calculate a limit as b approaches a. And with the second approach, here's our formula for calculating the secant line connecting 2 points that are h units apart, and we simply want that value h to shrink to 0. Now we have to do limits here. We have to let h get closer and closer to 0. We can't let h actually take on the value 0 again, because we would have division by 0 here. Similarly, up here, we have to let b get closer and closer to a. We can't let b become a, because once it does, this difference becomes 0 and you have division by 0. Now both of these formulas give you the instantaneous rate of change of the function at x equals a. There is another notation for this. The function in question is f, so we put f, then a single apostrophe, and then we say of a. This is a notation that's read f prime of a, and it represents the instantaneous rate of change in f at x equals a. We can say the same thing for this one. Two different methods for finding the same quantity. Okay, let's put these formulas to practice on the next page. Consider the function f of x equals negative 1/2 x squared plus 3x. The graph of it is here on the right. Find the average rate of change of the function over the interval 2 to b. X equals 2 is here, and then we want to go to some arbitrary location to the right and call that location b. This gives us two different points on the curve, which I can connect and make this red secant line. Well, to find a formula for the slope of the secant line, we have m sub sec is equal to, we would plug b into the function to get the second output, minus plug 2 into the function to get the first output, and then divide this by the difference of the inputs, b minus 2. So to determine what f of b is, I simply plug b in for all the x's of the function. That gives me negative 1/2 b squared plus 3b. And now I want to subtract from this f of 2. So brackets, plug 2 into the function, negative 1/2 of 2 squared, that's negative 1/2 of 4, and then plus 3 times 2 is a 6. And all of this is over b minus 2. Continuing, we get negative 1/2 b squared plus 3b minus, inside those brackets will be 6 minus 2, which is 4. That confirms what the graph is showing us, that when x is 2, the output is 4. Hence, we have this point right here. And this is all over b minus 2. Okay, and technically we're done. This is the formula that will give me the slope of the secant line. All you have to do is tell me what b is specifically. Now let's use technology to predict the instantaneous rate of change at x equals 2. So at x equals 2, I'm looking for the slope of a tangent line. Imagine the tangent line. I'm picturing that orange line, and we want to predict its slope. We're going to do that by letting b get closer and closer to 2 and plugging into our formula and use technology. In Desmos, you can click this plus sign and add a table. Let's change the first column to b, and for the second column, we'll type in the formula we've just constructed for the slope of the secant line. So negative 1/2 b squared plus 3b minus 4, all over b minus 2. And now I can input different values of b. In my drawing, let's let b be 5 to start. So our image would look like this, and we'd have a negative sloped line. With technology, plug in b equals 5, and we can see that the calculation gives us a slope of negative 1/2. Let's summarize this in our notes. So when b was 5, we had negative 0.5 or negative 1/2 as the slope of the secant line. Now let's let b get closer to 2. So visually, what if b was 3? Let's plug 3 into our table. We get a slope of positive 0.5, as expected from the visual. Now I'm going to get even closer to 2. When b is 2.1, we get 0.95 as the slope of the secant line. When b is 2.01, we get 0.995. When b is 2.001, we get a slope of 0.9995. This leads me to speculate that the closer b gets to 2, the slope of the secant line might be getting closer and closer to 1. Let's confirm this by using math methods to find the instantaneous rate of change when x is 2. So to find the slope of the tangent line when x is 2, we need to do a limit as b approaches 2 of this secant line formula. Now I can't just plug in 2 because then I'll have 0 over 0. So I must do some algebraic manipulation. To help me with this, I'm going to have to do some factoring and simplifying, but I don't love the fact that we have a negative fraction lead coefficient. So I'm actually going to begin by multiplying the top and bottom of this formula by negative 2. That will make the b squared have a positive 1 coefficient, making my factoring easier. So we get b squared minus 6b plus 8 all over, And then in the denominator, I'll leave the negative 2 factored out. I'm going to factor the numerator. I can guess one of the factors will be b minus 2, meaning the other one would have to be b minus 4, so that when you FOIL these two terms, b minus 4 times b minus 2, you do want to confirm that that does in fact equal b squared minus 6b plus 8, which it does. So I have a correct factoring. Furthermore, the b minus 2's will now cancel, changing my expression to b minus 4 over negative 2. Now when I did the simplification, I effectively removed a removable discontinuity. This simplified function here is continuous when b is 2, whereas the previous step was not. It had a discontinuity there. But now that I have a continuous version, I can plug in b equals 2, giving me 2 minus 4, which is negative 2, over another negative 2, which in the end gives me a positive 1. That confirms my assumption over here that the slopes were getting closer to positive 1, and it doesn't seem to contradict the tangent line I was able to imagine ahead of time. It appears to have a slope of around 1, and it does have a slope of 1. Okay, on the next page, we're going to do the same problem, but we're going to use the alternate approach. Moving on. We have the same function here. This time, however, our interval will be from 2 to 2 plus h instead of 2 to b. So we have x equals 2. We go to the right some amount h to take us to 2 plus h. Again, that gives us 2 points, and I can draw a secant line. The slope of the secant line is given by f of 2 plus h minus f of 2 all over h. So to do this part here, I want to plug 2 plus h in for all the x's in this function. There's two different x's. Both x's will be replaced with the 2 plus h. So this gives me negative 1/2 parentheses 2 plus h and parentheses and then square that. And then plus 3 times parentheses 2 plus h. And this is the result of doing f of 2 plus h. We still have to remove f of 2, which we've already calculated earlier, and we got 4. So remove 4, and this is all over in h. So this is a formula that will give me the slope of the secant line if all you know is h. Let's use technology to predict the instantaneous rate of change at x equals 2. I'll make a new table. H will be the first header, and then I'll type in this whole thing and put a similar table in my notes. Let's let h be 3 to begin. That means I want to start at 2, but then go 3 units to the right. Our secant line would look something like this. Plugging 3 for h into our table, we get a slope of negative 0.5 or negative 1/2, confirming our visual of a negative slope. Let's shrink h to 1. So if h is 1, our visual looks like this. Plug 1 into our table, we get 0.5. And we want h to shrink towards 0 to approximate the slope of the tangent line. So get close to 0, 0.1 gives me a slope of 0.95. Closer to 0 for h, 0.01 gives me 0.995. Even closer to 0 gets a slope even closer to a slope of 1. So we can see as h tends to 0, the slopes appear to be approaching 1 again, confirming what we already know about the slope of the tangent line when x is 2. And now, let's confirm this using mathematical tools to find the instantaneous rate of change when x is 2. So the slope of the tangent line when x is 2 can be found by doing a limit as h goes to 0 of this formula for the slope of the secant line. Now I can't just plug in h equals 0 because I'll have division by 0, so I have to algebraically manipulate this and factor so I can cancel that denominator h. I'm going to begin by FOILing 2 plus h squared and also at the same time distributing 3 through these parentheses. So the negative 1/2 stays, parentheses, FOIL 2 plus h, we get 4 plus 4h plus h squared. Distribute the 3, we get plus 6 plus 3h, and then we have minus 4 all over h. Now I'll distribute the negative 1/2 through these parentheses, giving us negative 2 minus 2h minus 1/2 h squared, and then the rest. Notice we have minus 2, minus 4, and positive 6. Those all cancel. And the minus 2h and the positive 3h become positive h. So we're left with negative 1/2 h squared plus h all over h. And now I can factor in h out and cancel with the h down below. So we have a limit as h goes to 0 of negative 1/2 h plus 1. This function is continuous at h equals 0, even though the step before had a removable discontinuity at h equals 0. I'm now going to plug 0 in for h in the continuous version. That gives me a final limit of 1, again confirming the slope of the tangent line when x is 2 is 1. Now in general, moving forward, you can use either approach when trying to find the slope of a tangent line at a specific value. Okay, let's go to the next page. Predict and then find the instantaneous rates of change indicated below. So our first example, we have g of x equals 2x cubed plus 1 with its graph here. This notation is g prime of 1, and it stands for finding the instantaneous rate of change in the function g at x equals 1. So when x equals 1, we have a point on this curve. The output appears to be 3. It would be easy to confirm. g of 1 is 1 cubed is 1 times 2, and then add 1, we get 3, confirming that this is the point 1 comma 3. Now you have to imagine a tangent line. This line is not a tangent line. It does go through the point 1, 3, but it does not indicate how steep the curve is. This line is a better approximation of what the tangent line would be. Clearly it has a positive slope. A quick review of slopes. Horizontal lines have slope 0. Vertical lines, the slope does not exist. Lines that make 45 degrees right there. In other words, if you go right 1, you go up 1, have a slope of 1. If you go right 1, down 1, you get a slope of negative 1. Slopes of lines that in this blue area, such as this one, are between 1 and infinity. In this orange region, such as this line, those lines are between 0 and 1. In this region, such as this line, slopes are between negative 1 and 0. And then lines in the gray area, such as that one, slopes are between negative infinity and negative 1. Well, the slope of our orange tangent line in this picture is clearly more than 1. If we were to extend it and found where it hit the y-axis, perhaps at negative 2, for example, we could do a run of 1 followed by a rise of 5. If that were the case and our drawing is accurate, I might guess that our slope is around 5. We will find it now exactly. Let's do the formula that involves h approaching 0. So g prime of 1 can be found by doing a limit as h tends to 0 of g of, and we are interested at x equals 1, so I put a 1 here, plus h, and then minus g of 1, and then all over h. Now to evaluate g of 1 plus h, we plug in 1 plus h in for all the x's in the rule of g. So we get 2, and then change x to 1 plus h, and then cubed, and then plus 1. So this part of the formula gives us this part in our setup, and then we have minus, and then g of 1. We've already found g of 1. G of 1 is 3, and this is all over h. On the side here, let's calculate 1 plus h cubed by interpreting it as 1 plus h times itself 3 times. Let's FOIL the first pairing. We get 1 plus h, that's plus 2h, plus h squared. And now we got to distribute again. This 1 will distribute, and then this h will distribute. Distributing the 1 first, now distributing the h, and gather any like terms. We have h cubed, we have h squared plus 2h squared, that's 3h squared. H plus 2h is 3h, and then plus 1. This is the result of cubing 1 plus h. So back to the context of our problem. We have the 2 in front. Cube 1 plus h gives us this expression. Then we have a plus a 1 and then a minus a 3, all over an h. Now distribute this 2 across all 4 of those terms. And notice when I do 2 times 1, I'll get a 2, and then add a 1 will give a 3, and then subtract a 3 will cancel. So all the constants will cancel, leaving us with this expression. And now I can factor in h and cancel with the h in the denominator. Now I have a version of the function that's continuous at h equals 0, so I can substitute 0 in for these remaining h's, giving us 0 plus 0 plus 6. So g prime of 1 is actually 6, and not 5 like I guessed. Okay, let's look at this next example, h of x. H of x is our square root of x graph. We want h prime of 4, so we want the slope of the tangent line when x is 4. So the point in question is right here. This is the point 4, 2. 2 is confirmed by plugging 4 into the function, and square root of 4 is 2. So then do your best to draw some sort of straight line that looks like it's the correct tangent line. And it appears that the slope of this line would be starting here, right 4, up 1. So my current guess is that the slope of this tangent line is about 1/4. Rise over run. Well, let's confirm. Since we're using h for the name of the function, and for variety's sake, I'm going to use the b version to find h prime of 4. So this would be a limit as b approaches 4 of h of b minus h of 4 all over b minus 4. So h of b is just square root of b, and h of 4 is 2. Now to simplify this one, we're going to rationalize the numerator. So I'm going to multiply the numerator and denominator by the conjugate of the numerator, which will be radical b plus 2. Now I'll FOIL the numerator, but I'll leave the denominator factored. Radical b times radical b is b, plus 2 radical b, and then minus 2 radical b, and then minus 4. All over, and then leave factored b minus 4 times radical b plus 2. Well, this term and this term are going to cancel each other, which always happens when you FOIL conjugates, giving us a limit as b goes to 4 of b minus 4 over itself times rad b plus 2. Cancel these next. I will finally get a function that is continuous at b equals 4. So I can plug in 4 for b right now. Square root of 4 is 2, add 2, and sure enough, we do get 1/4. This time confirming what my guess was. So I can put 1/4 here as an answer and change these wavy equal signs to exactly equal signs. The slope of the tangent line was in fact 1/4. Okay, let's do the next page. We have the graph of 1 over x and then shifted down 2. So there is a horizontal asymptote at y equals -2. In particular, we want the slope of the tangent line when x is -2 as well, which corresponds to this location. So I'm expecting a tangent line to look something like this. This is a negative slope tangent line, not quite as low as -1 slope. So I'm expecting a slope to be between -1 and 0. Let's just say that for the moment. Now setting this up, I'll go back to our h approaching 0 approach. M prime of -2, so the slope of the tangent line to the graph of m at x equals -2 is equal to a limit as h tends to 0 of m of -2 plus h minus m of -2 all over h. So now we've got to do this part of our formula, which means change this 1x here to -2 plus h, which gives us 1 over -2 plus h, and then minus 2. And then minus, and now we got to plug -2 into the function m, and that gives us -1/2 minus 2. And this is all over h. Now when this negative distributes, there's going to be a plus 2, meaning this -2 and this -2 are going to wind up canceling each other after I distribute the subtraction. So that takes us to this expression. I still can't plug in h equals 0. This is a complex fraction. I'm going to multiply the top and bottom by the LCD of all the subfractions. So the product of these two denominators will be that LCD. So I need to multiply by 2 times -2 plus h. Distribute and simplify through the numerator, but leave the denominator factored. So we get 2 plus, and then -2 plus h, all over h times 2 times -2 plus h. Then we're going to see we can cancel these 2's, and then we can cancel this h over h. Make sure you cancel in that order. That leaves us with a limit as h goes to 0 of 1 over 2 times -2 plus h. At this point, it is safe to plug in h equals 0, and when I do that, I get a final answer of -1/4. An answer I feel good with given our visual. And then lastly, we have a function p of x equals e to the x, and we want to find p prime of 0. Well, the point in question is 0, 1. Here's my attempt at a tangent line, and it does appear like the tangent line probably has a slope of around 1. Let's confirm. P prime of 0, so the slope of the tangent line to the function p of x at x equals 0. Let's use the h approaching 0 method. It's the limit as h goes to 0 of p of 0 plus h minus p of 0 all over h. Well, 0 plus h is just h, and then plug h into the p function, and we get e to the h, minus plug 0 into the p function, we get e to the 0, which is 1, over an h. If I try to plug in 0 now, I do get 0 over 0, and this is a case for which we do not have algebraic methods for simplifying or factoring, so I can cancel that denominator h. So instead, I'm going to use a table of points and let h get close to 0. I'll start close to 0 at 0.1. When h is 0.1, I use technology to calculate. Rounded to 4 decimals, I get 1.0517. Let's go even smaller for h. 0.01, I get 1.0050. Even smaller, I get 1.0005. And even smaller, I get 1.00005. And this is enough evidence to suggest to me that as h shrinks to 0, that our slope does appear to be approaching 1, as expected from the visual. So at this point, I'm going to conjecture that p prime of 0 is 1. Later in this course, we will confirm this fact. Okay, and this concludes our lesson on rates of change.